In today's lesson, we're going to learn about a change of base formula, which is a log formula that we use to find the missing exponent so that we can skip all of these steps that we did here in the do now. In our first example, we have an equation that says 4 to the x power equals 128. So if we use the method that we had in the do now, which is guess and check, we could just start plugging in values for x and finding out which one comes out to be the exact value of that exponent. So we'll start off with 4 squared, that's 16. So I'll keep going. 4 to the third, 64, I'll keep going. 4 to the fourth is 256. And then we see that we kind of have a problem here. So if we're looking for 128, that would be somewhere in between 64 and 256. So what that means is our exponent that we're looking for is not a whole number. It's going to be some number between 3 and 4. So we can just start guessing numbers between 3 and 4, but if you think in terms of decimals, there are a lot of numbers that it could be. So I'm going to just pick what's halfway between 3 and 4, and I'm going to find 4 to the power of 3.5 and see what that comes to. And in my calculator, it comes out to 128, which is what we were looking for. So that means the exponent here, the value of it was 3.5. Now that wasn't too difficult to find because we only tried one number in between 3 and 4. But what if it wasn't 3.5? What if it was something a bit more extreme like 3.6728 and so on? We're never going to be able to just guess that number. So instead, we come up with this formula that we use that we can type straight into the calculator, and the answer comes out without having to guess and check a bunch of different exponents. So in this example here, we have log base 15 of 162 equals x. What is the missing part? Well, we can see here that the missing part is our exponent, right? The exponent is on the other side of the log. So let's rewrite this in our exponent form, and then we can solve for our missing value. So we have 15 is our base, x is our exponent, and 162 is our result. So we can start to do what we did in the last problem by kind of using some guess and check and seeing what it comes to. So we'll start off, well, we know 15 to the first power is 15. 15 to the second power, if you type it in your calculator, it'll come to 225. So already we have an issue because we're looking for 162, and it's the same issue we had in the last problem. It's going to be somewhere between 1 and 2. So in the last problem, we just picked the number that's right in between. It was between 3 and 4, so I tried 3.5. In this problem, I'm looking for something that's between 1 and 2, so I'm going to try 1.5 and see what happens. So if I type in my calculator 15 to the power of 1.5, or 1.5, it comes out to 58.094 and so on, which is still not even 162. So now we know it's not going to be 1.5 as our answer, so it's going to be something a little bit bigger, but instead of picking 1.6, 1.7, 1.8, and still guessing with a bunch of different numbers, that's when we start to use this formula called change of base. So when you can't estimate it based on picking something in between, that's when we have to use this formula. So this is what the change of base formula is. And if you're wondering why it's called change of base formula, it is because we have a base that we cannot find the exponent for that will come out exactly the same as our result. So instead, we put it into a different base, which is something our calculator can understand. So each of our calculators, whether you're using the Casio calculator, the TI calculator, one of the apps, or even on the browser, each of them are in a standard base of 10. Okay, so when our base is not 10, like in that last example it was 15, we have to turn the base into a number that our calculator can understand so we can press that log button in the calculator. So if you're wondering what I mean, on our calculators, we have a log button. It's right next to the 7 on this version of the calculator. If you're using the Casio calculator like we do in school, it's right underneath the x squared button. If you have any other calculators, just look around. It'll say the word log somewhere on it. And it's somewhere around the area of the x squared button. So if I press the log button here, it doesn't give me an option to type in any base. So you'll see it just says log, and then it opens up a set of parentheses for you to type the next part in. But it doesn't give you an opening to put some number down in the base position. And that's because our calculators are set in standard of a base 10. So for us to solve these equations using our calculator, we have to turn our equations into a base 10. So what that means is we use this formula. And this formula converts it into a base 10 where our calculator can understand. We'll type this in and our answer will come out and we'll have the value of our exponent. So let's practice with this example here. We have x equals log base 9 of 71. Now if you were to try to solve this over on the side like we normally do, you would notice your guess and check method doesn't work because there is no exponent you can raise 9 to that will give you a value of 71. So that means it's going to be a decimal. So 9 to the x power equals 71 will have to be solved using this formula. So what we do with the formula is the value of your exponent will be equal to the log of the result, which in this case was 71, and we are going to divide it by the log of the base, which in this case was 9. Now, I suggest turning every log equation into an exponential first because it's easier for you to see the base and the result that way, and it's also easier for you to solve it if it is an easy question that you know the exponent for. In this case, we don't know the exponent, so that's when we use the formula. So we have log of 71 divided by log of 9. So I'm going to go back to my calculator, and I'm going to type exactly that in. I'm going to type the button that says log, 71, and then I'm going to divide it by log of my base, which was 9. And it comes out to 1.9400, so on. So we can take this, and let's say we'll round it to the nearest hundredths place. We'll take this answer, round it to the nearest hundredths place, and that should be our exponent. So in this case, it would be 1.94. So the value here is 1.94. Now, if I want to check that answer, remember, we did round, so our answer is not going to come out exact, but it should come out pretty close to 71 if I were to check it in this exponential equation. So if I go back here in my calculator and I type in 9 to the power of 1.94, which is what we just got as our answer, it comes out pretty close to 71. It says 70.995. So it's pretty close to 71, which is what our answer should be, which means our check proves our answer makes sense. So we go back here. 1.94 would be our answer. Now, of course, there's no way for me to just start guess and check and come out to get not 1.94 without trying a whole bunch of different numbers and taking a very long time. So that's why this formula exists, so you don't have to guess and check. So if we go back to this question we had before with the 15, we know it's not exponent 1, we know it's not an exponent of 2, it's something in between, but instead of using guess and check like we did here, we're just going to use the change of base formula. Now, change of base formula says the exponent will be equal to the log of the result, which in this case was 162, divided by the log of the base, which in this case was 15. I'm going to type that in my calculator, and I get log of 162 divided by log of 15, and it comes out to 1.87869. Now, you'll see we guessed 1.5 before, so we weren't even close. And for us to actually eventually guess 1.878, it's almost impossible. It's probably impossible. So instead, we use this formula, and now we'll just round our answer to the nearest hundredths place, or whatever the question asks for. I'm just going to say hundredths for this. So 1.87869 will be 1.88. And I'm pretty sure under here I did say nearest hundredths place, so that's good. So our exponent will be 1.88.